Hey again, folks. Here's the next problem for the playlist. It's kind of a weird one. We have this fish that's attached to a spring for some reason. And in part A, we're going to let it drop 0.05 meters and then check what the speed is. Once we're done with that, we need to figure out what the maximum speed could be for the remaining part. Now, why would we attach a fish to a spring and do this? I have absolutely no idea. I don't write the problems, I'm just here to help you solve them. My only request is that you please don't do this to any fish in real life. Anyways, let's grab our energy conservation equation. Before the fish drops, it's at rest. So the initial kinetic energy has to be 0. There's no friction occurring or anything like that, so we can set the other work term to 0 as well. That leaves just the following. Let's take a closer look at these. On the left, the potential energy shows up as potential energy of position, since the fish is hanging out above what we're calling y is equal to 0. On the right, mgy disappears, and instead we have the elastic potential energy of the spring due to the fish's weight acting on it and stretching it out. Let's start solving for this v variable. I'll move the elastic potential energy of the spring from the right over to the other side. Then we can multiply both sides by 2, divide both sides by the mass, and then take the square root. If we plug in the numbers carefully, our calculator will report the same as the book answer using 3 significant figures. Part A is now done. For part B, we'll have to think about how we could influence the falling speed of this fish. We can't change the fish's mass or the spring constant, and we certainly can't change the acceleration due to gravity. We can, however, change the falling distance, y. That means if we took a derivative of the final kinetic energy with respect to y, and if we set that equal to 0, it would tell us how high we would have to drop the fish from in order to get the maximum speed. The kinetic energy expression itself doesn't have any y terms in it, but we did say that it was equal to the difference of the potential energies in part A, when I move that one term from the right over to the left. These quantities definitely have y terms in them, so we're good. We can keep going. When we apply the power rule of derivatives here, we'll get the following expression. The 2 and the 1/2 will cancel each other out, and if we move this ky piece over to the other side and then divide both sides by k, now we know how far the fish needs to drop in terms of defined quantities. Let's go back to that kinetic energy expression that we had. Instead of writing y in these terms on the right, we'll plug in mg over k, like this. mg will become squared in this first term, and this k coefficient out front here in the second term will be canceled out by one of the k's in the denominator. Normally, I'd say that we should get a common denominator for this type of situation here, but check this out. If we bring the 1/2 mv squared part back into the picture, since that's what this is equal to, we can multiply both sides by 2 which takes care of a common denominator issue. Notice there's a mass attached to all these terms again. So let's cancel out a single factor of that on both sides. I'll subtract a single mg squared over k from this first term, which has two of them, and that will leave only one. Now we can take the square root of both sides, and we're ready to start plugging in numbers and finish things up. When we do that, we match the book's answer of approximately 0.566 meters per second. And now part B is complete. That's it for today. Have a great day, everybody.